We've now spoken about crude separation of proteins, followed by some purification techniques such as dialysis and maybe an affinity chromatography column. But once we've gone through all of those separations, we of course want to know, do we have our protein in purity in our sample? And what is the rough molecular weight of the protein? We want to be able to recognize that the steps that we've gone through to purify it have worked and that we have the right thing there, and molecular weight is one way we can look for that. So let's look at a technique called Sds Page, or sodium dodecyl sulfate polyacrylamide gel electrophoresis. It's quite a mouthful, but we usually just use Sds Page, and let's look at how that works as you are performing your own Sds Page gel today. If we had two electrodes, so we know we would be looking at a cathode and an anode, and the electrical current would pass through a buffer, and I'm just going to draw an upper buffer reservoir into which we could say that one of these electrodes was placed. So this electrode would be our cathode, or our negatively charged electrode. And then we would see a lower buffer reservoir into which our positively charged electrode, or our anode, would be placed. And then we have this gel, a polyacrylamide gel. And we're going to load our protein into wells in the gel. And if we were just looking at a regular old electrophoresis, a polyacrylamide gel into which we hadn't added any SDS, or sodium dodecyl sulfate, we would just take our proteins and let's just draw a cartoon drawing of a protein. And if we say that the buffer in this solution was slightly alkaline, we would know that our protein would be above the pKa for many of the residues, and it would take on an overall negative charge. So say that we did load our protein into one of these wells, and we knew that it was negatively charged, we would know that it would migrate through the gel from the cathode to the anode, traveling, as you would guess, towards the charge it was attracted to. Now, what's interesting is that if we're just looking at a regular polyacrylamide gel electrophoresis, the separation through this gel is going to be based, yes, on charge, but it is additionally going to be based on size. So both size and charge are going to dictate the rate of migration through the gel. If we want to, as we just stated, separate this protein based only upon size, then we would have to get creative. We would have to denature this protein and add in, and this detergent, sodium dodecyl sulfate, would have a dual purpose of denaturing the protein, and additionally, because SDS, and let me just draw you a picture of what this detergent looks like. As all good detergents do, it has a polar head group and a long hydrocarbon tail. In fact, it's got 12 carbons. So this tail of 12 carbons makes this an amphipathic molecule, a polar head group, a long side chain, and we know this to be true of good detergents. But what this detergent does is twofold. It causes the protein to denature, but additionally it binds to the protein in a ratio of 1 molecule of SDS to every 2 amino acids. So what that does is that it evens out the charge on every protein so that it negates the influence of charge on migration. So we get a separation that is based upon size alone. So this is a little bit tricky to draw, but if we use our creative minds, we could say now in the presence of SDS, this protein would be just denatured. Then the SDS would bind to this denatured protein, and it'll bind 1 SDS molecule for every 2 residues or 2 amino acids, therefore negating the effect of charge, making it so that the charge to mass ratio is equivalent in proteins, and therefore allowing for the separation based upon size alone. So this denatured protein could be loaded into the well, and of course the charge factor would be negated, and so the large proteins would move very, very slowly through the gel, whereas the small proteins would move very rapidly. So when you stopped the progress of the gel, a very small protein would have traveled very far, whereas a very large protein would have not. And of course, for those of you who are excited to see an equation expressing that rate, it's just going to be equal to 1 over the log of molecular weight. So you can see that inverse factor where as the size gets larger, the rate gets slower. So in SDS Page, we're able to separate proteins based upon size alone.